All right, let's use the second derivative to find the intervals where this function is concave up and concave down. And so for this we need the second derivative. So we're first going to find the first derivative. So f prime of x is going to equal the first times derivative of the second, which is e to the negative x, plus second e to the negative x times the derivative of the first, which is 1. I'm going to factor out an e to the negative x. Now we'll get negative x plus 1. This is for f prime of x. Now I'm not looking in this problem to find intervals of increase or decrease, so I'm going to go right to finding the second derivative, which is what is going to help me find intervals of concavity. And so I'm going to just use a product rule here. So first would be negative e to the negative x times derivative of the second, which would be just negative 1, plus second times derivative of the first, which is negative e to the negative x. I'm going to simplify and factor. So I have negative e to the negative x. When I distribute, I'm going to get plus e to the negative x. And there's an x there. It's going to be positive x e to the negative x minus e to the negative x. I'm going to combine like terms. I'm going to get x e to the negative x minus 2e to the negative x. This is my second derivative. I want to set this equal to 0 because I want to find out, using the same process as where we find intervals of increase and decrease, but we are looking for concavity. So I can factor out an e to the negative x, and I'm left with x minus 2. Now e to the negative x is never equal to 0. That's an exponential function. You should know what that looks like. A little rough sketch looks like that. It doesn't actually hit that x-axis. The x-axis is actually a horizontal asymptote. So what I know is that this second derivative is equal to 0 only when x equals 2. So I'm going to use do my test values. 2 is where the second derivative is equal to 0. The domain, by the way, of this function is all real numbers, so I don't have to worry about any values not being part of the domain. So I could test to the left at 1 and to the right at 3. And I'm testing the second derivative, the sign of the second derivative. And so since e to the negative x is always positive, I really only care about the sign of x minus 2. So when I plug in a 1 here, I get negative, right? So the second derivative is negative when x equals 1. When I plug in a 3, I get a positive. And so what I know is that the second derivative is negative from negative infinity to 2 and positive from 2 to infinity. That means the function f is concave up on the interval from 2 to infinity, because that's where the second derivative is positive. It's concave down from negative infinity to 2. And where you have a sign change in your concavity or in your second derivative, as long as that value is in the domain, your function is defined there, you're going to have what we call an inflection point. And there is an inflection point, or a point of inflection, at x equals 2. So let's graph that function. X times e to the negative x. I'm going to just do a zoom 6, just a standard window, and see how that looks, and we can play around with that after if we need to. So when we graph x e to the negative x, the window is a little, we might have to zoom in on this a little bit to see what's going on. So what I want to do, I care about what's happening at 2. That's where the concavity changes from concave down to concave up. So basically concave down looks like this, concave up looks like that. Sometimes it's a little more subtle. So let's look at this picture. I'm going to trace on 2, hit enter, and I'm going to zoom in right there. So I traced, I'm going to zoom in so I can see this picture a little bit better. And again, it's very subtle here, but what's happening is that this function is concave down from to the left of 2, and it's hard to see. This is starting to become concave up. I may change my window a little bit so I can see the picture a little bit better. So I played around with my window until I got a picture that was a little easier to see. I have an x min of 0, x max of 10, scale of 1, a y min of 0, a y max of 1, and a scale of 1. When I graph that, you see the picture a little bit clearer. I'm going to trace on 2 and hit enter. And you can see here the function is concave down, right? When we get to 2, and the function is concave up after 2. The point right here is called an inflection point, and that's where your function changes concavity. Okay, let's look at per B. We'll look at a polynomial here. Same thing, we want to find out the intervals where this function is concave up, concave down, and where there are any inflection points. The domain for this function is all real numbers since it's a polynomial. I'm going to find my first derivative, f prime of x, is equal to 12x cubed minus 12x squared minus 12x plus 12. My second derivative would be 36x squared minus 24x minus 12, and I want to set that equal to 0. Before I do anything here, I can factor out a 12, or I can divide all these terms by 12. You're allowed to divide by a constant without losing any solutions. So I'm going to rewrite this as 3x squared minus 2x minus 1 equals 0. This is factorable. It factors as 3x with an x, and this is going to be minus 1, and this will be plus 1. Setting both of those factors equal to 0, I get x is equal to negative 1/3 and x is equal to positive 1. And so when I'm testing intervals, and again this is my second derivative I'm testing, I'm going to test at negative 1/3, or that's an endpoint of an interval. So I'm going to test to the left of negative 1/3, which would be negative 1. I'll test between negative 1/3 and 0. And I will test to the right of 0, which is 2. Now I'm plugging in these values, the test values, into the second derivative, which is right here, 3x plus 1, x minus 1. When I plug in negative 1, this is going to be negative 3 plus 1. This is going to be negative, and this is going to be negative. So I would have a positive here. When I plug in 0, this is going to be positive, this is going to be negative, so I've got negative in here. When I plug in 2, this is going to be positive, this is also going to be positive, so the second derivative would be positive here. So I know that the function is concave up from negative infinity up through negative 1/3, union 1 to infinity. I know the function is concave down, and that is from negative 1/3 to 1, and I have inflection points at x equals negative 1/3, where we change signs, and at x equals 1, where we also change signs. So let's do the same thing. Let's graph this function and just confirm that our analytical work is correct. So I've graphed the function, and I can see the window that I have. I think the window on the x is a little off. I'd rather shrink this a little bit or zoom in on a little bit. Instead of going from negative 10 to 10, I think I can go even from negative 5 to 5 will probably give me a better picture here. So negative 5, and then the max will be 5. I'm going to graph that. All right, so when I look at my intervals, we claimed that the function was concave up from negative infinity to negative 1/3. So let's trace on negative 1/3. Right. And we can see there we are, and actually maybe if I change where I've got these values here, it's nice to have them, but sometimes you have to make your y, change your y scale a bit. So I'm going to go in my window and I'm going to change that a little bit. I'm going to go from, say, negative 20 down to positive 20. And we'll go and graph that again and get a little better picture. Once I hit trace, negative 1 divided by 3, there we go, we can see that a little better. So what we've got here, we said we are concave up, or our function's concave up from negative infinity up through to negative 1/3. We have a change in concavity, or an inflection point at negative 1/3, and from negative 1/3 to 1, we're concave down. That's why we have a negative. And from 1 to infinity, we are concave up, but the function is concave up. So the graph confirms our analytical work.